Welcome back. This video is about log functions, and to motivate them, let's take a look at this expression 2 to the power of x is equal to 5 and think about the solutions for it. It can't be 2. X cannot be 2 since 2 to the 2 is equal to 4. That's too small. It can't be 3. 2 to the power of 3 is equal to 8. That's too big. We know that the exponential function b to the power of x looks like this, has that shape. It's always increasing as we go left to right. So know that the answer has to be somewhere between x is equal to 2 and x is equal to 3. It's got to be somewhere in the middle, somewhere in here, between 2 and 3, where we get that y value of 5. But where exactly is not something that we have mathematical equipment to answer. And that's what this is about, the section about introducing that equipment, which is something called a log function. For the exponential relationship b to the power of y equals x, for base b greater than 0 and b not equal to 1, we will define a new function that allows us to interchange the locations of what variable is being plugged in and which variable is isolated. So that function that does that, or that function that allows you to isolate for the y that's currently in the exponent, is the log function. B to the power of y equals x means the same thing as y equals log base b of x. Before you get too weirded out, you've seen this before. So if you have, let's say, an expression like this, 2 to the power of 3 is equal to 8. We're used to writing this equivalently as cube root of 8 equals 2. Those two statements mean the same thing. 2 is equal to cube root of 8 is an equivalent statement to 2 to the power of 3 equals 8. We do something similar with logs. We can say 2 to the power of 3 equals 8 can be rewritten as 3 equals log base 2 of 8. So in the top example, the cube root function is introduced as a new type of function. In the bottom example, above the log there, we have, in the bottom example, we have the log function being introduced as a new type of function. Its role is analogous. It's just, it gives us a tool for isolating for a variable. One thing to watch for is that you can't plug any negative numbers into a log function. The domain of the log function is only positive x. X must be greater than 0. That's the domain of all log functions, independent of the base. Now the log function is, by the way it's defined, it allows us to immediately create log properties. These are kind of like translation rules. So looking at this thing here, at these rules for roots, we have a rule like this. If we have a cube root of x and raise that to the power of 3, we get x back. This is called an inverse function property. Cube rooting something is the opposite of raising it to the power of 3. Exponentiating something is the opposite of logging something. So because we have b to the y being equal to x and y equals log base b of x, because those two statements are equivalent, what we can do is, for example, I can replace this x here with this, since x equals b to the y. So that gives me the bottom one that says that y equals log base b of b to the y. That's called the cancellation law, one of the cancellation laws. And again, that's perfectly analogous to saying the cube root of x to the power of 3 is equal to x, or x to the power of 3 all cube rooted is equal to x. That's equivalent to that. It's just saying b to the power of y does something to y. Log base b does the opposite. If you do both things together, nothing happened to y. It's like walking 2 steps forward and walking 2 steps backwards. You end up where you started. We could also go the other way. we could take this b to the y here, or we could take this y here, rather. So this is y, this thing is y. Plug that then up in there for y. We have another cancellation law, which is b to the power of log base b of x equals x. So that's another so-called cancellation law. I'm going to label these because I didn't label them properly on the note. So this is a cancellation law. And the one in green is also a cancellation law. And nothing new is going on other than exactly what we have here with the cube roots. If we have a cube root of x cubed being equal to x, we're making the exact same type of statement. That cube rooting something and raising something to the power of 3 are opposite operations, and no change happens to the variable if we do both operations back to back. This is saying the same thing. It's the same type of cancellation law, but for exponential functions instead of for polynomial functions. And actually, I'll put that down. I'll put that down here. These are cancellation laws for polynomial functions. And these are cancellation laws for exponential functions. So some examples of the cancellation laws being used: log base 5 of 5 to the x is equal to x. We could just cancel the log base 5 and exponential base 5. They do opposite things to x. With concrete numbers, log base 9 of 9 to the 8, we can cancel log base 9 with exponential base 9 and just get what's being plugged in, just the 8. So let's use this logic, let's use these rules to simplify expressions like the following ones: log base 10 of 100. So we think, how can we access a cancellation law to simplify this expression? Well, in all the cancellation laws, the base of the log function matches the base of the exponential. So that's what we want to do. We want to make base of exponential match base of log. So I'm going to say, can I write 100 as 10 to a power? And the answer is yes. I can write it as 10 to the power of 2. Then I can use a cancellation law, and I'll just get the power. I'll get 2. You can type it into a calculator if you want to try it. Make sure you use the correct log button with base 10. Okay, next, log base 2 of 8. Well, we're going to do the same thing. Can I write 8 as 2 to a power? The answer is yes. I can write it as 2 to the power of 3. Then I can cancel, and I just get 3. Okay, the next one, I want to do something similar. I want to write 1 over 27 as 3 to a power. I'm going to do this one in 2 steps. This is log base 3 of 1 over 3 to the 3. So I can make that part the same. I can't cancel them. I cannot cancel them yet. It has to be exactly base to the same base to a power. Right now it's 1 over that same base to a power, so the rule doesn't apply. But if I use another law of exponents, I can write this as 3 to the power of minus 3. Positive power of the denominator becomes a negative power of the numerator. And now I can use the cancellation law. I just get negative 3. And I'll circle those answers. 2, 3, negative 3. And the last one. What do we do here? How do we cancel? Because there's no power, right? But there is. If there's no power in a number, what power is always there? The answer is 1. 99 to the power of 1. So we can cancel, and we're left with just a 1. So a good question to ask at this point is, what is a log function anyway? And the good answer to that question is, a log function is a function that behaves according to this cancellation law. That is, at this point, the best definition that exists for a log function. It has this rule. It has this special property. That's a log function. There's more to it than that, but let's start there. So as a result of this property, lots of confusion comes in. Sometimes we expect that the x is always inside the log, and we don't expect the x to be outside the log, or we don't expect x to appear in the base of the log. I like to think of the log expression as a type of translation. Like square roots and powers are a type of translation from one form to another form. Square roots or logs and exponentials are a type of translation, just like you would translate from English to French or French to English. So if I see a log expression and I'm confused, like y equals log base b of x, I'm free to translate it into the corresponding exponential expression. Remember that y equals log base b of x means that x equals b to the power of y. They are identical expressions. They encode the same information in different ways. So with some concrete numbers, 4 equals log base 2 of 16 looks kind of mysterious. It looks like not what we're used to seeing, but it's perfectly equivalent to, if we use that translation rule, it's perfectly equivalent to 16 is equal to 2 to the power of 4, which doesn't look weird at all. How about when we put x in the base of the log function, which we shouldn't do? We're actually not going to do that. I'm just doing this for the purposes of illustration. And I'll do one more example that's like this, but again, just to illustrate something. 3 equals log base x of 27. Like, solve for x. How on earth am I supposed to solve for x? I don't even know what a log function is. But yeah, you don't have to know what a log function is. All you have to do is translate it. So the 27, the thing's being currently plugged into a log function, that's all by itself. Then equals the base of a log function becomes the base of the exponential function. I mean, in this case, it isn't exponential because the base is the variable, but that's beside the point. So whatever was in the base becomes, wherever's in the base of the log becomes the base of the exponential. And then the thing that was all by itself becomes the power. So we can rewrite this as 27 is equal to x cubed, and now it becomes a very simple problem, as x is 3. So that's often the strategy that we will use to solve problems. We'll solve the problem by translating. So we have a choice for solving log questions. Choice 1 is to use the cancellation laws, or 2 is to translate from logs to exponentials. So this might be French, this might be English, and there's a translation process that allows us to go from one language to another language, just like going from exponentials to logs or logs to exponentials, depending on what suits us for solving the problem at hand. It's worth revisiting everything now. Like, once we introduce these new functions and these new operations, which I'm about to tell you about, it's worth going back and thinking about all of our operations. So if you have an expression that starts with a equals b, what can you do to that expression that does not break the equality, does not break the equal sign? One thing you can do is you can add something to both sides. So for example, you're free to add 5 to both sides and nothing will change. You're also free to subtract the same thing from both sides. So subtract 3 from both sides, and the equal sign will not be violated. Something else you can do to both sides is multiplication. You can multiply both sides by a constant, like 5. Or you can divide both sides by a constant, like 2. You just don't want to divide by 0. Another operation that can be done with some care is squaring. You can square both sides, or you can cube both sides, raise both sides to a power of 3. Those operations will again not destroy the equal sign. The equal sign will be left equals. Square roots and cube roots and fourth roots, roots can be taken on both sides. As long as you're not taking the root of a negative or an even root of a negative number, then you're going to create an undefined operation. Those are all operations that we've already used throughout the course. The new ones at the bottom of the slide may cause you some concern, but they're perfectly valid. The first one at the bottom, the first new one, is called exponentiation. If a is equal to b, it turns out that 2 to the a is equal to 2 to the b, or 3 to the a is equal to 3 to the b. And actually, we've already done this, but we did it in reverse. We took the expressions that looked like 2 to the a is equal to 2 to the b and said, well, that means a is equal to b. Well, we could go backwards. If a is equal to b, that means pick any base you want. 7 to the a is equal to that same base, 7 to the power of b. We're going to use this type of operation, this exponentiation operation, in order to access the cancellation law. So this is done in order to access cancellation law. The cancellation law is so powerful and so valuable that we're willing to exponentiate both sides of an expression in order to get access to it. The last one on this slide is called logging. Logging both sides. If a is equal to b, as long as both sides are positive, then the log of a is going to be equal to the log of b. And why would we do this? Why would we take something perfectly good like a is equal to b and then hit both sides with a log? And the answer is actually the same as the one above. It is to access the cancellation law. Because the cancellation law allows us to simplify. And we'll pick up on this application slide next, where we use those ideas, those logging and exponentiation ideas, or if you want, you can use translation ideas in order to solve for x that's trapped in a log function, or to rearrange an expression that involves logs, so it's a little bit less weird looking.